Hello, hello, my beautiful AP Calculus students. In this video, we will apply separation of variables to a differential equation in order to derive the law of exponential change. We will then recognize and use the law of exponential change to write and solve a single part of each of 3 different FRQs from previous AP Calculus AB exams. Example 1. Write and solve a differential equation when the rate of change of y with respect to x is proportional to y. So I want a differential equation. A differential equation is nothing more than an equation that has a derivative in it. And I'm looking at the wording of this question here, and I see something in here that indicates a derivative to me. When I think of derivative, I think of slope. When I think of slope, I think of what phrase? I hope you have it here, rate of change. So let's come up here. I'd like to underline this rate of change thing here. This indicates a derivative. A derivative of what? The derivative of y with respect to x, which is very logical. We already know that the derivative of y with respect to x is written as dy dx. So I'm going to come over to the left and I'm going to say dy dx is equal to, I know that's coming up because it says is proportional to y. So normally when I hear the word proportional, I think of three different kinds of proportionality. I think of a direct proportion, or an inverse proportion, or maybe a joint proportion, and I don't see any of those words here. All I see is proportional to y. So if you don't see one of those words, the inferred word is direct. So this is directly proportional to y. If this question wanted me to do an inverse proportion or a joint proportion, it would have to tell me explicitly. It does not say that. So when you just see the word proportional, think directly proportional. Okay? So as we reread this now, write and solve a differential equation when the rate of change of y with respect to x is directly proportional to y. We know that this equation, dy dx, has to equal some constant multiplied by y. That's what a direct proportion is. Where k, I'm going to write here, where k is the constant of proportionality. Where k is the constant of proportionality. Very good. All right, so the first part of my problem is done. I found and I wrote a differential equation that represents the rate of change of y with respect to x being directly proportional to y. Very good. Now the second task is to solve this differential equation, which means they want to know what is the function whose derivative is a constant multiple of itself. So we have got to solve for y. This is a dy dx, so if you want to get y, obviously we're going to integrate someplace in here. But in order to integrate first, we are going to play around with separation of variables. And to do that, we need to get our y variables on the left-hand side of the equation and our x variables on the right-hand side of the equation. So step 1 is to multiply both sides of this equation by dx. This is going to yield dy is equal to ky dx. And now I got the x variable out of the left-hand side of the equation, so my next step here would be to get the y variable out of the right-hand side of the equation. So I need to divide both sides of this equation by y. This is going to yield 1 over y dy is equal to k dx. And now, since my variables are separated, I can go ahead and integrate both sides of the equations, of this equation. Now I know that you will most likely just throw integral symbols on the equation that's sitting there, but I would like to rewrite it. Integral of 1 over y dy is equal to the integral of k dx. That means that the integral of 1 over y with respect to y has to be equal to the integral of k with respect to x. You should recognize the left-hand side of this equation. This is nothing more than the natural log of the absolute value of y is equal to kx plus c. Hopefully that's okay with you. Let me see if I can explain that a little better for you. If I wanted to integrate, let's say the number 5, the constant 5 with respect to x, I would end up getting 5x because the derivative of 5x is just 5. So in this case, I want to integrate k with respect to x. I'm going to get kx plus c. And if I took this derivative, if I took the derivative of kx plus c, wouldn't the derivative of this simply bring me right back to k, and that is true. So we're going to just leave that right there like that. Now I still haven't solved for y, but I'm getting closer. Y is the power in this logarithmic equation. So I would like to switch from logarithmic form here into exponential form. I need to know what my base is, and I'm hoping everybody knows that the base here is nothing more than e. So I have e to the kx plus c is equal to the absolute value of y. This gives me, I like to turn this around and get my y on the left-hand side. The absolute value of y is equal to e to the kx plus c. And I really don't like this absolute value thing going on here. So if the absolute value of y equals e to the kx plus c, then doesn't y itself have to either be positive e to the kx plus c or negative e to the kx plus c, so that when you took its absolute value, you were back to itself again? So let's go ahead and write that. Y is equal to plus or minus e to the kx plus c. And now I'm going to take another couple little steps here and simplify this down. Even though I do have an equation for y, I don't like this mess that it looks like. So I'm going to clear this up a little bit and get to what's known as the law of exponential change here. This is y equals plus or minus e to the kx times e to the c. Now I know this typically, the first time you see this, blows your mind, but it really shouldn't. It's easier to take two powers that are being multiplied with a common base and know enough to add the exponents. So if you had e to the kx times e to the c, I don't think it would be a big jump for you to call that e to the kx plus c. It's going backwards that usually blows people's minds, but it's okay. We'll get used to it. If you have an exponent that has the sum or difference inside them, then you can break that up into two powers, either being multiplied or divided. In this case, divided. In this case, multiplied. So I hope you understand that. Hope that's okay for you. Okay, I can go to the side and do something a little easier for you, something like x squared times x cubed. I know you'd all say x to the fifth, but wouldn't you first say 2 plus 3 in your mind and then say fifth? So basically, instead of going forward here, I'm going backwards. And I'm saying I can take x to the 2 plus 3 and bring it backwards and call it x squared times x cubed. All right, let's get rid of all that. Okay, and now I am simply going to change position here. I'm going to call this e to the c times e to the kx. And I'm doing that on purpose because all of this stuff at the beginning here, all of this is nothing more than some other constant. So I'm going to let that be capital P e to the kx. And I'm finished with this problem. We now have, I'm going to erase this little circle here, we now have y is solved for in terms of x. And I can't do anything because I don't have any initial condition to solve for that p, so I'm pretty much done with that. So these two things are absolutely identical, which is kind of cool. I'm going to do this here. I'm going to take this first equation here, this derivative of y with respect to x is equal to some constant multiplied by y. And I'm going to let you know that these two expressions, or two equations if you will, are mathematically identical. This thing that we just found, this is coming up here too. This is the same thing as saying that y is equal to some constant p times e to the kx, which is pretty cool. Now, when we differentiate with respect to time, which normally we do differentiate with respect to time, we could rewrite this, and I'm going to do that. This is dy dt, because I'm differentiating y with respect to time now, is equal to ky, means the same thing as y equals p e to the k, and instead of an x, I'm using a t. This right here, this little tidbit, which is really, really important. This is known as your law of exponential change. And that is going to end this first example here. This is really cool because anytime a question gives us the fact that the rate of change of a value with respect to time is directly proportional to that value itself, instead of going through and writing a differential equation and solving the differential equation, we can just jump to the law of exponential change, which is going to be super cool. So before we move on, I want to chat with you about this formula a little bit and see if it rings a bell with any other formula that you've learned in the past. Do you think that you recognize this y equals PE to the KT formula? Perhaps we had some other letters in it, but it was the same basic formatting. I'm hoping that you're saying, yeah, that reminds me of that PERT formula we used in the past. And that formula was A equals PE to the RT. It would allow us to find the total balance left at the end of a certain time period, given a certain interest rate, compounded continuously. Remember when we were compounding continuously, we used this E formula. So I'm hoping this does ring a bell with you. So this, let's say for instance that we wanted to know the initial amount of a particular investment. Remember we would have something like some investment, or let me just say something like A equals, the initial investment would be this P here, like $1,000. E to the interest rate might be like 3%, so like 0.03 T. And we could figure out how much money we had left in the account after 5 years or 10 years or 20 years or so on. We could also say how long would it take before we had $10,000 in the account, stuff like that. We would use our graphing calculators to figure this out. So I'm hoping this rings a bell with you. Do you remember this $1,000 here? This 1,000 was the initial investment that we had. And that 1,000 turns out to be the initial investment because you can find the initial amount of something by letting t equal 0. So when time is 0, that's the beginning of your investment. And if we put 0 in here for this time, we would end up with 0.03 times 0, which would be 0 for an exponent. And e to the 0 is simply 1. So then the amount in the bank would be $1,000. The initial amount in the bank would be $1,000. So this P indicates the initial amount. Same thing happens up here. The P that's in this top equation up here, P ends up being the initial amount. And for the same reason, when you let t equal 0, so at t equals 0, the initial amount would end up being the P, because when you let this t value right here equal 0, then anything times 0 is 0, and then e to 0 turns into a 1, and you just end up with y equals P. So the initial amount, again, is your P value. Okay? And it is kind of neat that we use a P because it does backtrack to this formula that we had last year, and this whole thing here relates really well with that whole thing there. All right, so now we'll move on to question number 2. Example 2 reads, the rate of change of y with respect to time t is proportional to y. When t equals 0, y equals 2, and when t equals 2, y equals 4. What is the value of y when t equals 3? Well, I see a rate of change phrase in there that tells me I'm dealing with some kind of a differential equation. So I just, straightforward to me, I would think of going at this with a dy dt, right? Because I'm looking at rate of change being the derivative of y with respect to time t. So that is going to give me dy dt. Come back here with me, please. Thank you. So I'm looking at dy dt is equal to, because we have the rate of change of y with respect to time t is proportional to y. Again, that means is directly proportional to y. So that equals ky. And I look at this thing and I say, hey, wait a minute, I just got done doing that. And I found out that this ended up being mathematically equivalent to the law of exponential change. So now, instead of using this formula and having to work through and find my k and all that good stuff, play around, I think I am going to just switch this into y equals p e to the kt. And this is my law of exponential change. All right, now they give me t equals 0 y equals 2. When t equals 0, y equals 2. Now, if I'm real intuitive, I understand when t equals 0 that they are giving me the initial condition. This indicates the initial condition. This means that I have the point 0, 2 belonging to my function y. Now, if I'm really cool, I would know that that 2 is going to go right in for p, and that I could just write y equals 2 e to the kt, because of what we just got done discussing up here about how that p is the initial amount. Okay, so let's go back. Let's pretend we're not very intuitive and we forget about that whole idea. So we're not going to have this, and we're just going to think, oh, well, I have a combination of points here, 0, 2. So I'm going to write here using 0, 2, and we will actually solve this thing. We get a 2 equals p e to the k times 0. Well, I think everybody's going to be all right with this one. K times 0 is 0. Can you see it happening already? E to the 0 is 1. So therefore, my p is equal to 2. And I can go right back and write the equation now. All right. Y equals 2 e to the kt. But wouldn't it have been nice if we were super intuitive at the beginning? That would have saved us all that work, and we could have just jumped straight from the original question straight to this. Okay. Also, you know, I really didn't need to write this differential equation, because this law of exponential change is applicable anytime the rate of change of something with respect to time is proportional to itself. So anytime that happens, we can go ahead and jump right at the law of exponential change. All right, that being said, now I need to use my next condition. I need to use this fact here that t equals 2, y equals 4. So now I'm going to say using t equals 2, y equals 4. So my t is like my x. And I'm going to put this in here. This is 4 equals 2 e to the k times 2. I will divide both sides by 2 to eliminate that leading coefficient. And I'll get 2 equals e to the 2k. I think everything is looking right so far. Now I want to solve for k so I can put it back in my original formula and then use that information to get y when t equals 3. So I need that k out of the exponent. Right now this is written in exponential form. I am going to switch this into logarithmic form. This is going to give me natural log. Of course my base is e coming from this base. I don't have to write it though. So natural log of 2 is equal to 2k. Notice that my power has to go in my parentheses. Okay, when you take a base and raise it to an exponent, you get a power, so the 2 is the power. And I'm going to divide both sides by 2 to solve for k. This gives me k equals 1/2 natural log of 2. And if you'd like to call that 0.5 natural log of 2, that's fine as well. Alrighty, so let's do this. Let's bring this up here, and let's rewrite now. Y equals 2e to the kt. I don't want that to look like it might appear to be a greater than sign. It's not. And I'm going to place the k where it belongs in there. Y equals 2e to the 1/2 natural log of 2 times t. And that little asterisk is my time symbol. How's that? I know, probably not so good, but it's what it's going to be. Okay, let's clean this up a little bit. I know that a lot of you are thinking that 1/2 can go in and become a square root of 2, which is absolutely true. It could. The t can come out front. That's absolutely true as well. But I think I'm just going to leave that the way it is, and I'm going to use that t equals 3 part here. So now, at t equals 3, what is the y value? That's my question now. So I got y equals 2e to the 1/2, and you know, I think I'm going to drop a line just because I got too much mess going on there. Y equals 2e to the 1/2 natural log of 2 multiplied by 3. I'm going to take the 3 and I'm going to multiply by the 1/2. And now I could put this right in the calculator right the way it is, as a matter of fact. I just feel like cleaning it up. So that gives me 3/2, and 3/2 is like 1.5 natural log of 2. So I could say that this is my answer right here if I wanted to. Or I could throw it in the calculator and I could get an approximation for the y value. Let's do that. Throw that in my calculator. I end up with 5.656854249. And then I will use my rule of thumb and go 3 digits past the decimal and look to my 8. This is 5.657. So either of these two answers would work out just fine. All right. And yeah, I did not like how that came down so shaky. So question number 2 looks like it's done. What is the value of y when t equals 3? The y value is 2e to the 1.5 natural log of 2, or it's simply 5.657. You know, we could simplify this a little bit more too. I feel like I just want to do this with you, even though on an AP Calc test you should stop there. But just for practice, I just want you to see this. This is 2e to the natural log of 2 to the 1.5. And when you're doing e to the natural log of something, then that ends up just being 2 times 2 to the 1.5. And I suppose if you wanted to get a little more technical with that, we could actually call this, let me see, this is 2 to the first. So I could add my exponents here. Now what did I do here? I want this to be like this. This is 2 to the 2.5, which is indeed that decimal value again. So we could play around with that a little bit, but remember on AP Calc tests, they really don't want to see your arithmetic. They want to see your calculus, but I just couldn't help myself on that one. Okay, example 2 is done. Example 3. A puppy weighs 2.0 pounds at birth and 3.5 pounds 2 months later. If the weight of the puppy during its first 6 months is increasing at a rate proportional to its weight, then how much will the puppy weigh when it is 3 months old? So it looks like the first sentence is giving me some kind of measurements here that pair up with each other. So the puppy's going to weigh 2 pounds at birth, so that's like an initial condition. At t equals 0, the weight of the puppy is 2 pounds, and 3.5 pounds 2 months later. So when t equals 2 months, the weight of the puppy is 3.5 pounds. That's what I'm reading from that. So you know what, I think I'll write that down. At t equals 0, and we're talking months here. At t equals 0 months, weight equals 2.0 pounds. And additionally, at t equals how many months? 2 months later, the weight is 3.5 pounds. Very good. Okay, so that gives me a couple of pairs of coordinates to play with here, like the last question did. Now let's read the next sentence. If the weight of the puppy during its first 6 months is increasing at a rate proportional to its weight. So increasing means changing in the positive direction, but it is a rate of change we're talking about. So we're talking about a derivative. We're talking about the weight of the puppy changing at a rate proportional to the weight of the puppy, which is kind of crazy. This is one of those things we just got done talking about, and now we can turn around and we can refer to this as our law of exponential change. So we're going to write here that law of exponential change. We're going to write y equals p e to the kt, where y is the weight of the puppy, and t is time in months, right? We have a little restriction on our time as well, too, because it talks about if the weight of the puppy during its first 6 months. So in this case in particular, we were looking at 0 is less than or equal to t is less than or equal to 6 only. Alrighty. Well, here we go. We have got to take the information that's given to us, and we need to write an equation for y, and we're going to use that to plug in a 3 for t equals 3 months here. This last question says, how much will the puppy weigh when it is 3 months old? So we'll go back to that at one point. But first we need to write the equation. So do we know P or do we know K? Those are two unknowns that we have to solve for, and of course that's why they gave us two pieces of information up here. Well, I have this fact that at t equals 0, the weight is 2 pounds. So this is my initial weight, so to speak. So I can just go ahead and put that right in for P. This tells me right here that P equals 2. So I'm going to write y equals 2e to the kt. That's what the first set of, or that at t equals 0 months, the weight is 2.0 pounds. That's what that tells me. So I'm going to now use the next piece of information that I have. I'm going to say using my t value is a 2, and my y value in this case is going to end up being the weight of the puppy, which is 3.5 pounds. So now I'm going to use this xy coordinate point, or I should say xt, or ty coordinate point, I'm sorry, ty coordinate point, to figure out my k value. So my y is 3.5, I'm going to put a 3.5 in here, equals 2 e to the k times 2. So this is going to be 3.5 equals 2e to the 2k. Just to clean that up a little bit, I'll divide both sides by 2 to eliminate that leading coefficient. This gives me 1.75 equals e to the 2k. Okay, now I want to get k, and k is up in the exponent, so I want to bring it down. So I know that if you've used other resources, you probably have seen somebody tell you to apply the natural log to both sides of the equation, and that will do it. But this is an exponential form right now, and I'm just going to switch it into logarithmic form. This is going to give me, I'm going to scoot up a little bit here, this is going to give me the natural log of my power, which is 1.75, is equal to my exponent, which is 2k, because a logarithm is an exponent. Let's not forget that. And the base e that was over there is still here. I don't have to write it because it's understood to be an e if I don't write an e there. Now to solve for k, I simply divide both sides by 2, and I end up with k equals 1/2 natural log of 1.75. I'm going to take that together with this fact here, and I will rewrite my equation now. Y equals 2e to the 1/2 natural log of 1.75 times t. And that is my equation. And at this point I can say, okay, I want to know at t equals 3 months, what will be the weight of that puppy? So let's put a 3 in. We have y equals 2e to the 1/2 natural log of 1.75 times 3. And that's going to give me that 3/2, or that 1.5, if you will. I'm going to write 2e to the 1.5 natural log of 1.75. And I'm going to punch that into my calculator. I'm going to get a decimal approximation, which is 4.630064,794. And that will result in approximately, I'm going to go 3 digits here, so that's a 0. I'm going to look over at this 0, and I'm just going to get 4.630 pounds. And we're going to write pounds a little nicer than that. Very good. So I'm hoping that's kind of clear to you. It's kind of a straightforward question. Once you've done a couple of these, it gets a little bit easier and easier and easier. So example 3 is done. Does it make sense? At t equals 0, the puppy's 2 pounds. At t equals 2, the puppy's 3.5 pounds. At t equals 3 months. Yeah, I mean the puppy's growing, so I think it makes pretty good sense. Okay, moving on to example 4 then. A particular bacteria culture increases at a rate proportional to the number of bacteria present. Boom, that is definitely talking about my law of exponential change. If the number of bacteria doubles in 3 hours, how many hours will the number of bacteria triple? So the number of bacteria doubles in 3 hours. But I don't know the original number of bacteria, do I? So let's just start this out a little bit, and I don't think it even matters what the original amount is. I can pick any original amount as well. Do you remember we used to do these types of questions with having an investment at 4.2% interest? We wanted to know how long it would take for that investment to double. So it doesn't matter whether it's your investment or my investment or somebody else's investment. We can all invest different amounts, but the time it takes for any investment to double is the same time it takes for any other investment to double. So we're going to be able to choose any initial number of bacteria present in our culture, okay, or in our sample. Okay, so we're going to start off with, let's see, y equals p e to the kt. Do you recognize this as being the law of exponential growth? I hope so, because the bacteria is growing at a rate proportional to the bacteria, and that's when you can use this. Now, if it said a particular bacteria increases at a rate proportional to the square root of the bacteria present, we would not be able to use this formula. Or if it said to the square of the bacteria present, we would not be able to use this formula. But the particular bacteria culture is increasing at a rate proportional to the number of bacteria itself. So this is why we can use the exponential growth formula. All right, so what do we know? I can pick any, so you can choose any initial amount. I can't believe I just did that. For capital P. So I'm just going to pick one. Let's just say I have one bacteria, and I want to know when is this thing going to, it says if the number of bacteria doubles in 3 hours. So e to the k times, if I put a 3 here, that'd be 3 hours, and if I double the number 1, it becomes a number 2. So this is how I'm going to solve for k. I'm going to use the fact that the number of bacteria doubles in 3 hours. So this is going to just give me 2 equals e to the 3k. Again, this is exponential form, so I'm going to switch it into logarithmic form. This gives me natural log of 2 is equal to 3x. Divide both sides by 3. Oh, it's not 3x, it's 3 what? K, thank you. Divide both sides by 3, and k is equal to 1/3 the natural log of 2. Very good. I'm going to take that together with the fact that I started with a 1. Whoa, get back over here. I'm going to move my hand. Together with the fact that I started with a 1, I'm going to put this in here, and I'm going to say y equals 1 e to the kt. At this point, I'm going to replace my k with 1/3 natural log of 2 times t. And that's going to be the formula that I'm using before I apply the next piece. I'm going to clean that up just a little bit. Times t. So now I want to know how many hours will the number of bacteria triple. So if my initial bacteria is the number 1, then I triple 1, it becomes a 3. So I'm going to put 3 in for the number of bacteria. And I want to know how many hours is it going to take. That means I have to solve for my t, for time. When the question says how many hours, this is a t equals what problem. So this gives me 1/3 natural log of 2 times t. I need to figure out, solve for t. If I had a graphing calculator, I could do this real quick. I'd put the 3 into y1, and I'd put the right-hand side of my equation into y2, and I'd get my point of intersection. And that would be super fast. I'm going to go ahead and just continue simplifying this down a little bit, because it's possible that this could be a multiple choice question, and they don't give you decimal values, that they actually give you natural log problem or answers instead. So we're going to go ahead and see if we can solve for this. I'm going to clean this up slightly. This gives me 3 equals e to the, can I call this t over 3 natural log of 2? And now I'm going to switch this again from exponential into logarithmic form. So I'm looking at natural log of 3 is equal to t divided by 3 natural log of 2. Okay, multiply both sides by 3 to eliminate that fraction, and I have 3 natural log of 3 is equal to t natural log of 2. Divide both sides by whatever's attached to your t, natural log of 2, divide by natural log of 2. And this is going to, you know what, I think I will just leave that right there and come up over here. And I will say that 3 natural log of 3 divided by natural log of 2 is equal to my t. And I can just see an AP question not leaving it this way, but instead taking this coefficient on the outside of my logarithm and bringing it up as an exponent inside my power. So I'm guessing that this would be more like 3 cubed, natural log of 3 cubed over the natural log of 2, which gives me a final answer of natural log of 27 divided by the natural log of 2. And you might want to think you can divide the 27 by the 2, but you can't. And you wouldn't turn this into subtraction either. That would be getting the rule backwards. This would be our final answer. Now, if I pop that in a calculator, I would get a t-value of approximately 4.7548875 hours. So rounding to 3 decimal places here, that would give me t is approximately 4.755 hours. And either of these answers would be good. Now, since I used a graphing calculator to put the natural log of 27 divided by the natural log of 2 into my calculator, it seems to me I would go right back up to this step right here, and I would throw that in my calculator to make sure that my point of intersection did indeed have an x value of 4.755, which I'm sure it will. All right, well, that ends example 4. I hope everybody is a little less intimidated by these questions, and I hope that you can look at a problem and distinguish whether or not the exponential or the law of exponential growth applies to the problem or not. And that wraps up our session on the law of exponential change, y equals p e to the kt. One last thing, talent out.